Good morning. How are you doing? Approximately. So today we will have a longer break after lunch. We resume at I think 5:30, and there's no exercise session. So you may profit. I think it's a sunny day today. Don't get lost. And those who want to swim, they should make a photograph to prove that they have been swimming. Okay? But be back at 5:30. I mean 5:25. Okay? So I decided to change my program. I wanted to talk originally about algebraic power series today and tensorialization, but I think it's better to provide additional information for the talk of Dorian Popescu. So today I will talk a little bit about flat maps and about regular maps, and then I will start directly with Artin approximation. So, as usual, I won't give a complete description of these concepts. I just want to give you the abstract definition and the geometry, and then you have to combine. So, if you want to get frustrated, I suggest you to look at the Stacks project, and then you find thousands of equivalent characterizations of flat morphisms, of regular morphisms, of whatever. So it's not easy to find a good reference. Yeah? I will be using Atiyah MacDonald a little bit, and I will just give you the top of the iceberg. Okay. So this is lecture 3. And we will continue on ring maps. And we start, so we have two concepts to discuss, flat morphisms and regular morphisms. So let us start with flat morphisms or maps. So I will use the word morphism whenever I talk of geometry, and maps when I talk of ring maps. Okay? So I will start this time with geometry and then go back to algebra. So assume that you have given a morphism of algebraic varieties f from x to y. You could also take schemes if you want, doesn't matter, or analytic varieties with fibers x, y, y, and y, though x, y is just the inverse image of y. So this is closed inside x, and this will describe x as a disjoint union of all these fibers. Okay. And let me draw a picture. Maybe we take the following. this correct? Hopefully. This is dotted. Okay, here you see the surface. I hope you see it. So this is x. And you take for y just the line, and you project vertically. So you will get, as fibers, you will get these nodes here. Okay. So here you have y, you have x of y. And then, as you move y, this family of varieties will vary. So this can be seen as a family of varieties indexed by y in y. Okay. So, and you will see that you will have a special fiber here, which is a cusp, let's say at y0. So, whenever you are outside y0, this looks quite similar, and then you get a different shape, and then it starts to be nodes again. And the purpose of flatness is to describe a certain good behavior of this family of fibers. And what you want is a kind of continuity of the fibers, but this continuity is not well defined because the fibers are not points of a topological space. So instead of using a topology, you use flatness. Okay? So the goal is define what it means that the fibers xy vary continuously. Which means they should not jump. Whatever this means, don't jump. And you have seen in the exercises already yesterday an example. If you take the projection of the union of the coordinate axis to the line, then you will see that the special fiber xy0 is a line, whereas xy is just a point. Okay. So here, the dimension of the fibers jumps, and this should be a family which is not flat. Dimension of fibers jumps, and this is certainly not continuous. Again, my continuous is not defined. It's just on the heuristic level. But if you rotate this coordinate axis and you project again, y0, then outside this point you get a fiber consisting of 2 points, and in y0 you will get 1 point, but you count it double because it's an intersection point. So this will be continuous. Variation of fibers. Okay? And the concept of flatness makes this precise. So flatness is an algebraic method to describe the continuity of the fibers. Okay? I guess that many of you are familiar with the concept of flatness. So we now pass to the coordinate rings. And so we now take the following definition. Let R to S be a ring map. And if you don't mind, I call it again F, even though it would be the dual map of this F over there, but we are generous. Okay? A ring map. So I'm not going to define flatness for modules. I will just do it for ring extensions. So S becomes an R module. So that S becomes an R module. And S is flat, or S is flat over R, or F is a flat map, if and only if. Tensorizing R modules with S over R is an exact functor. So what does this mean? So I will only look at short exact sequences for all short exact sequences of R modules 0 M N L 0. The induced sequence zero is again exact. So I remember when I saw this definition for the first time, I think I was doing my PhD or something, yes. Then I just decided I don't want to know this. But then the topic of my thesis required to understand it a little bit. So there are many equivalent definitions, and I will give you two of them. The next one is almost as abstract as this one, but then I will give you one where you can really work with. So for all I in R finitely generated ideal, the map, if you tensorize I with S over R and you send it to S, so you take here H, tensor, let's say S, and you just multiply, this map is injective.
So this is true for our non-Euclidean theorem.
Don't ask me about non-Euclidean rings, please. But I think it's true in general, because otherwise you would not need this here. Yeah. Okay. So you can do the theory in the most generality, but Guillaume.
I just want to mention that this function is right exact general, so wrong exact. Injective morphism do not remain injective after tensorialism.
Yes, but I just want to give you this definition to show that there's an abstract definition. I don't ask you to understand this. I will give you the definition you have to understand afterwards. Okay? Okay. So so the funny thing is that being flat is part of Artin approximation theorem. We will come to this a little bit later. So a couple of remarks. If S is free over R as an R module, then it is flat over R. B, if you localize R, you get a flat extension. U in R multiplicatively closed. Then R going to S equals U inverse R is flat. And C, all this can be proven by using the properties of tensorization and exact sequences. Flatness is preserved under direct limits and inverse limits. Flatness is compatible with limits. We only need a special case. So, in particular, if Rm is a local ring with completion, R hat, the inverse limit R m to the k, then R to R hat, the natural map going to the completion, is flat. So this applies typically. Now we have already several.
One question.
Yes.
You wrote compatible with limits, and you said with injective and projective limits, right?
Yes.
Okay.
Yes.
So it's compatible with
Yes. Typically, R is k x1n xn. You have a localization of the polynomial ring. R is x1 xn, or R is k x1 xn. All these rings are local Noetherian rings, and in all three cases R hat is just the formal power series ring. Okay? And this, if you now take a quotient of the such an ideal by an ideal, such a ring by an ideal, you also get the quotient of the formal power series ring by the ideal, completed ideal, and then it holds again. But I just mentioned these cases. Okay.
Why is R modulo NK flat? I mean, compatible with.
Yeah. Exercise. Or Paco will know. Good exercise. So now we have the following lemma. Now I give you a characterization of flatness in terms of relations. So we need let H1, Hk be in R elements. Denote by rel R H Hk. So this will be a submodule of the Cartesian product, the relation module between these elements. Module of H1 Hk. So this Hk are vectors R1, Rk in R to the k, some Ri, Hi equals 0. Okay. You take the linear relations between these elements. It's in general, it's hard to compute these relations. Yeah? You saw one exercise where I asked you to compute the linear relations, but it's not so, I mean, abstractly it is at least clear that it exists. And then R is, no, S is flat over R for all ideals I of R, all H1, Hk in I. Now, think of S as being a ring extension of R, as we have it here. Okay? So we can look at the relations between H1 up to Hk in S and in R. Of course, in S we will have more relations because S is larger. Okay? And the condition is that the relations over S between H1, Hk, so that any linear relation actually stems from a relation in R. So this is generated over S by the R module of R relations. Well, R H1 Hk. So by this I denote the S module generated.
The idea of I is useful.
You're right, but It's not useful, but I like ideals. Okay. So HK. No, I take the module generated by S. Yeah. Yeah, it's something like the tenth. Yeah. You extend the scalars. I will give an example. Okay. Example, we take R kx1 xn, R S R hat kx1 xn, take convergent h1 of x, hk of x in k of x. So we take convergent power series, but we look at the relations which are formal. And a formal power series relation. And now I don't write R, I will write y1 of x, yk of x in kx. So we have some hi of x, yi hat of x equals 0. Okay? And then the claim is that these formal relations are actually linear combinations of the convergent ones. Okay. Then these y hat of x, y1 of x, yk of x are formal linear combinations By formal, I mean over kx. Linear combinations of convergent relations. So this is a result you have seen in Guillaume's lecture. Do you see the connection with Guillaume's lecture? Compare with Ploski's result in the linear case. Ploski gives you a parameterization nearby a formal solution, and here you get even a better description. You get a description of all formal solutions in terms of the convergent ones. Okay, this is for me. Compare with Ploski's result. Okay. So in particular, as these are linear combinations of the convergent ones, get in particular there exists convergent relation y of x in kx to the k, some hi of x, y of x, 0, I equals 1 to k. And then by an extra trick you can make yi coincide with yi hat up to any prescribed degree. But that's not necessary, as Popescu and Guillaume hinted out. So this gives you Artin for linear equations. This answers the Artin approximation problem, or resolves for linear homogeneous equations. Homogeneous in the sense that we have no constant term on the right-hand side. Okay? So this is just general nonsense. You use the compatibility of flatness with limits, and you get it for free. Okay?
And in a bit of math, we say that flatness is localization maps are flat. So if you take the ring of polynomial, you localize the maximal ideal, and then you make a compilation, it's also flat.
Yes.
You can do the same.
Yes.
It's still true for R, the ring of polynomial.
Yes.
But Artin approximation theorem is not true.
Right.
Yes. In the linear case, you can even find rational relations, whereas in general not. Okay? So, maybe just a remark. If H1, Hk are in Kx as before, but if you have an additional one, and also H0 is in Kx, and we want to solve the linear inhomogeneous equation. Now, instead of equating everything to 0, we ask that some hi of x, yi, I from 1 to k equals h0 of x. Now this is a slightly more general situation, because now you have a term on the right hand side. Then the same argument works, but you have to assume a little bit more than this solvability. Problem. So this solvability is expressed so this solvability problem maybe is expressed by a stronger version than flatness, which is called faithful flatness. By the faithful flatness of R hat over R. So faithful flatness means for a ring map that the functor of tensorization is faithful exact. So it sends exact sequences to exact sequences, and conversely. Yeah? The induced sequence being exact, although the original sequence is exact. I'm not going to go into this, but this also holds for the completion. Also true for completions. Of local rings. So this is a relation of flatness to the linear situation in Artin approximation. I want to give you a final geometric interpretation to flatness in terms of families of fibers, families of varieties. This is not necessary for Artin, but it gives you another feeling for flatness. Now I change a little bit the notation. Maybe I call them Fi again. Yeah. F1 of Tx, Fk of Tx in K Tx be power series depending. Now I want to treat T as a parameter depending on a parameter T in some space T. You could just take A1K. Doesn't matter. So if you want, you can write, for each T, you get something in X. Okay? So you can consider xt. Now, take care. I write T for the variable, and I also write T for the point, for the parameter value. Whenever we fix a T, we can look at xt, which will be just V of F sub T, Ft inverse of 0. Okay? This will be in A and K for T in T. So now you really see the family of fibers, of varieties. This is the family of varieties. It's analytic varieties, but you may also take polynomials, doesn't matter. Okay? You have a family of varieties, and you want to express this flatness for this family xt. And the flatness is a local property. Let T0 in T be a chosen point. Then the family xt T near T0, so this is the germ of the family. So I draw, here you have T, here you have xt, here you have T0. Okay, you have a family of varieties, let's say curves. And this corresponds to a morphism. I let it up to you to express this as a morphism of rings. Then xt is a flat local family. Local in the sense for T nearby T0 if any relation R0 of x in Kx K. Now you specify T equal to T0, any relation R0 of x, this is a vector of convergent power series between F1 T0x up to Ft Fk T0x. So R0 has k components and the linear combination gives 0. If any relation R0 lifts to a relation RT of x now you could also write this as Rtx in k txk between, and now you pass from the specific point t0 to an arbitrary point f1 tx fk tx.
Excuse me?
Yes.
So if you write ft to the minus 1, 0, you mean f to the minus 1, t comma 0, right?
Here?
Yeah.
This is just the zero set.
Of
It's
this
confusing because we have indices from 1 to k and you have the indices of t.
F is the vector, and I use again t. T is in the field, and 1 to k are natural numbers, so I use both. You are intelligent enough to distinguish what I mean. Okay? Yeah. So the example, though this is a certain continuity of the ideals, you take, now I write it in terms of ideals, t times x. This is an ideal in even polynomial ktx. It's a silly example, but still. So you just have one f here, and you take t0 equals 0. So what happens? For t0, 0, you have f0x is 0, and everything is a relation. R0 is, for instance, 1. Okay? But you are not able to lift this t different 0 relation does not lift. Because outside 0, you have no relation at all. You just have a single element, so it's boiled down to a trivial situation, but the geometry is very nice, because for t equals 0, the 0 set is the whole line. So this is x0. Yeah, this vanishes. But whenever t is non-zero, x has to be 0. So outside, so you have t equals 0, but for t different 0, you just get a point. Okay, and this is the example from the exercises. And it's the first example where you see a jump in the dimension. Okay? Here, this point here is xt. Think about it. I'm not going to explain this more. Okay? So this is a little bit about flatness. I think that's all I want to say about flatness. No, there was one more thing. I think I can erase. Do we have questions about the flatness? Oh yes, I have to add one remark. So, fact, if xt, now I just write t in t. I write it in this suggestive way of a family of varieties. If this is a flat family, of varieties, then, so as there is no precise concept of continuity, you try to get close to it. And one corollary is that the fiber dimension is constant. Dimension xt is constant for t in t. So that's already good. Fiber dimension cannot jump. Now, if you if you take fibers which have singularities, then something I cannot express in detail, the multiplicity of the singularities of xt are constant for t in t, and more generally, the Hilbert-Samuel function is constant. Hilbert function, for those who know of xt, is constant. Okay? And do you remember yesterday in the lecture of Dorin, he had this flatness assumption in his theorem in the definition of regular morphisms. So, if, in particular, if all xt are smooth varieties, then flatness of xt implies again constant dimension. Okay, so this example is excluded. This is an example where the fibers jump, no? So if you have a family of smooth varieties and they are flat, then this looks like a fiber bundle. Then X, the space of all xt, looks like a fiber bundle. Fiber, or if you even want, vector bundle. And I tried to draw it. Let's say the dimension is 2. So maybe you have something like this. And then the next one, all these are the fibers. They all look quite similar. Maybe they move a little bit. And here you have t, xt. I hope you see the picture. This, like this, okay? So if a family of sheets all have the same dimension, and they look like being isomorphic to each other, okay? So this is a situation where Dorin will talk about, but not for finitely generated algebras, but for more general ones, okay? So this is all I want to say about flatness, I think.
May I have a question?
Yes.
In the second statement.
The multiplicity.
No, I think it's not. It is unknown in positive correctly.
If the multiplicity is constant, ah, very good.
I have tried to formulate the group, analytic group to special standard group.
Ah, very good. So this is exercise.
Even I was
Now that's very interesting.
even when I was
So the proof of the constancy requires characteristic 0 in the analytic category.
Sorry. If the base is a PBR,
Yes?
the flatness coincides with no torsion.
Yes.
So you can have a variety over generic fiber with smooth and over the special fiber is single. So that will produce a variety of change.
No, but the Hilbert-Samuel function is constant.
Yes.
But then it...
It means that, for instance, you have an elliptic curve which becomes flat.
Yes, I agree, but something is wrong then here.
The function remains constant because
It's not the local Hilbert.
Okay, in any case, we won't use this. So it was just an additional information. So maybe you can give us a reference where this can be read in more details.
Action.
Okay.
So what's the time? Ah. So for the regular morphism or regular maps, I just want to give you the definition. I'm not going to discuss this. This is again a big topic. Regular maps. Again, I start geometrically. F from x to y, a morphism between, so I only can give you the feeling. I'm not doing mathematics here. Yeah? You have to do it yourself. Between algebraic varieties is regular. All fibers x, y, y and y are smooth varieties. So I work here over an algebraically closed field, not to have to distinguish between smooth and regular varieties. So if you prefer, you can say regular varieties. And so it's just the picture I erased. Okay, the regular morphism is all fibers are smooth, and there's one notion which is often used, which is geometrically regular. F is geometrically regular. If this is true after base field extension, F remains regular after base field extension. Please don't worry too much about this. Again, this is a delicate concept if you are in characteristic P. But in general, regular morphisms, just think about it, something about the fibers are nice and smooth. Okay? And algebraically, so many people only give this algebraically. So you have F from R to S, a ring map. And then I always mix up the letters. And you ask also, sorry. F is flat plus. Sorry. You also require flatness, which means constancy of the fiber dimension. And algebraically, this means you have a ring map, and F is regular, and accordingly also geometrically regular. F is flat, so S is flat over R, and for all P in R prime, for all Q in S prime, F inverse of Q equal to P. So you take primes which are lying over P. You have the fiber, so the fiber is expressed through the tensor product, the fiber ring, as localized in Q mod P times SQ, and this is the same SQ tensor over R, the residue field of P with K, P, RP mod P times RP, the residue field are regular local rings. Okay. Again, you have characterizations and so on, and the Jacobian criterion, but just to give you a little bit of information about what Dorian will talk about. I think I don't want to say much more about regular maps. This should suffice for the moment. Okay, so this is the end of lecture 2, which was extended till today. And for the last half an hour, I will start with lecture 3, the true lecture 3. And now things will become a little bit more difficult. Yes? Yes. I would like to postpone this to the exercises. Yeah? It is a ring of a smooth variety. Okay? So it means that, I mean, then you have to do the theory of regular rings, but I would need 15 minutes to explain it now. Okay? I think there are many students here who know it, and maybe you communicate among yourself what it means. So now, this was the part on ring maps, and now Artin approximation from a geometric viewpoint. So now you can forget everything I have talked about, and what I want to do in the remainder of the time of today and tomorrow is the following. Let f of x1, xn, y1 up to ym in k, x, y to the k be a vector of convergent or formal. We will do it simultaneously for both convergent and formal power series, but to give you more feeling, we take it convergent of convergent or formal power series. So let R be k of x and Rn. Now this is the Cartesian product. Sorry, Rm. This will be now vectors of power series y1 of x, ym of x, yi of x, and kx. Okay. And the goal is describe the structure of the following. we take y of x. Now, sometimes I will write it like this, sometimes I will write it with r, whatever I prefer. We take all y of x vectors such that f of x, y of x is identically 0. Yes?
These y's are vanishing at the origin.
That's what I was just going to say, but you can say it. So, I'm not going to quote this all the times, but whenever I substitute, I will assume tacitly that y of 0 is 0, but I don't want to put it in the notation because this makes everything heavy. Okay, whenever you have a problem in substituting, assume that the constant terms are 0. Okay? So this is a huge, big thing. Okay? And of course, you could also look at, or the formal thing would be the formal power series solutions. Okay? So what is the geometry of y? And if we understand the geometry, the hope is that we have proven Artin. And the first case is the one we already did. If the vector f is linear in y, if f x y sum hi x yi plus h0 of x is linear, a linear polynomial vector in y1, ym. So now the hi are themselves vectors, but I don't use external notation. If these are linear, then by flatness, what is written here, we perfectly understand what's going on. Then y, what will be y? It's just this space of solutions. So it is this set of equations. Now hi are vectors. As it is inhomogeneous, you just take one particular solution, and then you will have the homogeneous solutions. So this will be particular solution plus, I don't know how, maybe I should call this y0, which is the y of x in k x to the m, sum hi of x, yi of x equals 0. So these are the homogeneous solutions. Okay? And this is well understood by flatness of r hat over r, or by, so I wanted to do this now, but I don't have time, so I give it to you, because it's an alternative proof. If you don't like flatness, you can prove it directly, or by lemma 1-2, chapter 6, in Rui's book, Basic Theory of Power Series. It's really worth to look it up. It's half a page. It's completely elementary. It's a proof to show that whenever you have a formal solution, you also have a convergent ones. So this would be Artin in the linear case. Okay? So as you understand perfectly well the linear case, the idea is to reduce to the linear case. Reduce the general case to the linear case. And this reduction is quite difficult, and I will try to explain you a little bit the ideas how to do this. Is this sufficient? Almost. You are very quiet today. Either you are already sleepy, or exhausted, or you don't understand anything, or bored. So you will remember one exercise. So remember exercise. I think it was the following: y of x cubed minus z of x squared equals, no, maybe it was t, but now I call it x. Let's say x squared. Okay? It was with t and t to the k. You remember this exercise? And the trick was, you write y of x as 1, or maybe a constant times y tilde of x, z of x 1 plus z tilde of x, where now y tilde of 0 is 0, z tilde of 0 is 0, and then you apply Taylor expansion, and get something like I think it was 3 y tilde of x plus minus 2 z tilde of x minus equals 0. Something like this. Higher order terms. Is it correct, Helen? Okay. And then we quoted the implicit functor theorem, then solve by using the implicit functor theorem, and you get, so you can choose any z tilde and you solve for y tilde uniquely. Okay? So choose z tilde x freely and solve for y tilde of x uniquely. everything is at the origin, x equals 0. This whole theory takes place locally around 0 in affine space. So Guillaume also said that you try to use the implicit function theorem, and we will use it in a more sophisticated way. Instead, yes.
You put the x squared into the higher order terms, or?
Yes. We can write here x squared, yeah. We have done it in the exercises, so I don't want to do it. Instead, we can do the following. Eliminate all higher order terms of the equation by a suitable automorphism of, now y tilde and z tilde belong both to the power series ring, so we are inside kx times kx. Here the elements are y tilde of x, z tilde of x. Of course, you should take again the power series which have no constant term, but I don't care here. So always, maybe you put here 0 to indicate that I only take power series with non-constant term. And now the whole procedure will be, on this infinite dimensional space, we will define a category of maps between such spaces. These maps will be analytic maps in infinite dimensional spaces, and we will have a notion of automorphism and diffeomorphism. So we will send this to something, actually, I'm cheating a little bit, we apply a power series to y tilde and z tilde, and then this change in y tilde and z tilde will allow to eliminate the higher order terms, and we have a linear part. So eliminate all higher order terms of the equation by a suitable automorphism, thus reducing to a linear equation. So this, now I'm going a little bit slowly here because this is maybe new stuff for you. So instead of working on this example, I will rephrase this. In terms of a commutative diagram. And in this commutative diagram, I am using now not only commutative algebra, I will use differential geometry, but differential geometry in an infinite dimensional setting. Using differential geometry in an infinite dimensional setting. So what you usually do for algebraic varieties in the finite dimensional setting, you copy this now here, but you have to make precise that everything works well. So we have f in k xy to the k, and this map induces a map from k x m. M is the number of y variables, okay, to k x k. So up to now we have only looked at ring maps. Now we look at analytic maps between rings or Cartesian products of rings. We take a vector y of x, and again y of 0 will be 0. We take a vector and we plug it in here. So we send it to f of x, y of x.
So it's not really enough
Because I don't write this one. Let me be a little bit loose. This is always very annoying, this 0 and so. Yeah. I would have to add here the maximal ideal, but then the notation becomes very annoying. I cheat a little bit. Excuse me. So let's take, for f, just take m example, m equals 1, f of x, y, k equals 1, x squared y plus x y cubed plus exp of x y to the 5th plus, I don't know, something, y to the 29, some power series. Now you have a power series in two sets of variables, and the f of x, y of x is just x squared y of x plus x y of x cubed plus exp of x y of x to the 5th, and so on. You substitute in the power series. So this map here is not linear, not at all. Yeah, it is given by substitution. That's what we could call an analytic map. Okay? And Artin approximation asks for the 0 set of this equals 0. Now you want to find all y of x having here 0. So it just looks at the fibers of this map. And maybe I call this f sharp. It is induced by f. And maybe you place yourself nearby a given formal solution. So you can do this equally for the formal power series. Okay, I don't write it. And this idea means the following. These maps are not defined globally, but I don't want to write the neighborhoods where they are defined. You try to find in the space of solutions what I would like to call a diffeomorphism. Diffeomorphism. So of course this is not defined yet because we are now in infinite dimensional spaces. But it should be something which behaves well in the sense that it has an inverse. Okay? So it is bijective. And it should have the following property. It should send convergent power series to convergent power series and formal power series to formal power series. Okay? And then you get here an induced map which will be phi inverse composed with f sharp. Okay.
Sorry, so is phi homomorphism of k double brackets x?
It will be defined so that it applies in both situations. You see here, already this map can also be applied to the formal power series rings. So it's of a similar type. I will do this not today, but in the last. I just want to give you a very general idea. So you try to find a diffeomorphism here, which is, we can give it explicitly. And this map here will become linear. linear in the sense of over here. In this sense. Okay? So where phi maps kx m to kxm and kxm to kxm and is continuous with respect to the M-adic topology. Okay? So this is the object we want to construct. It's not clear how to do this, but if we can find such a phi, then we can do the following. Then our set Y is just f sharp inverse of 0. This was the definition. Okay? But this is a general principle of commutative diagrams. The inverse image here, you take the inverse image here and you apply phi inverse. Okay? So this is equal phi inverse of, let me call this L sharp because it's linear, of L sharp inverse 0. So phi inverse, maybe we call this V. Okay? So this V is the solution set of this type of equation. Here you have V. And here, for the linear, so this is what I would call a linear space, or a fine, so this is linear. So we know Artin for this one. Okay? But phi behaves well with respect to completion. So we immediately get the description of Y. Okay? We understand V. So if we can construct phi explicitly, we also understand Y. Okay. And I have no blackboard left, but I conclude what we will show is so the result, which is not precise, but I will give you just the idea. So the result, which is a description of Y as an infinite dimensional variety, Y will be locally isomorphic to a Cartesian product I'm not specifying what I mean by locally. So this is a very big object there will be some capital Y times L, where Y is a finite dimensional algebraic variety, finite dimensional algebraic singular variety, or if you want, scheme. So that's why I gave you the exercises on Cartesian products, to make you a little bit familiar with Cartesian products. So you will have a finite dimensional factor which is singular, and the L will be a manifold. This will be an infinite dimensional manifold. Okay. So actually you can think of even of a linear space, even if you want linear space. Okay. So a linear space in the sense of a, say, it's of the form K, X, R. Something like this. It's just a power series space. So you have a finite dimensional part and an infinite dimensional part. And now if you understand this geometry and you want to see Artin approximation inside this geometric context, you say the following: a solution here splits into a finite dimensional part and an infinite dimensional part. In the infinite dimensional part, I have no problems because I am in a linear space. I can solve easily. And in the finite dimensional part, I have problems. But if I go with my power series to sufficiently high degree, I will leave this finite dimensional part. I'm here and I can solve. So this is the consequence. If we can solve f of x, y equals 0 up to sufficiently high degree, so this means modulo x to the c, or maybe I should write here x to the e. If we can solve this up to sufficiently high degree, then there's no more abstraction to solve. Then we can solve it completely. No more abstraction.
Yes.
But this is locally.
I wrote it here.
Yeah,
Locally, I wrote it.
consequence is also locally.
Oh, yes.
I mean, the E is not the same where depending where you are.
Yes.
So I will try to give you some more precise information. This was now, of course, very vague and imprecise. It's just a general idea. I will give you some ideas how this is done, and this in turn will reprove Artin approximation by understanding the geometry. Okay? So this will be the program of the last lecture.
How effective is this? So, give me an example like this where you have algebraic equations. Can you somehow compute in principle from me?
So in one variable, if you have one x variable, you have a certain chance to control something. But if you have several x variables, you have to use again induction on the number of variables, and then you lose any control. Okay? Good. We have finished for today. Thank you. And we have, yeah.